Okay, so we're just looking for where to get the trend line back. Okay, so polynomial 2, I'm going to display that one as well. Okay, so this is the equation. This right here is the equation for if this correlation were to be quadratic. And now let's add one more trend line. So I'm going to go from the start again. So add trend line, more trend line options. Okay, I'm going to add polynomial, but this time I'm going to add cubic. So that's going to be order 3, right? X to the third. And I'm going to display both of these on the graph itself. Okay, I'll just put that down there in the corner. Let's enlarge this so we can see what's going on. Okay, and that actually, if we take a look, both the squared and the cubic, so the quadratic and the cubic, do quite well for this. They're very accurate curves of best fit. Okay, and going up here, let's just take a look. Let's add that exponential back there. So actually, this exponential, I was thinking that the exponential would go and like taper off, but for the curve of best fit, it's actually going up, and these points are a little bit off compared. I mean, this is still a really, really strong curve of best fit, but compared to these ones, absolutely, like these are the x squared and the x cubed, so the quadratic and the cubic are almost touching every single point. So let's go back to the actual question. Find the quadratic regression in the form in basically x squared and record the coefficient of determination, r squared. So that's what we have under each one of these. That's the r squared, the correlation coefficient, the coefficient of determination, 0.99, and then we have 0.99 as well here. Whereas the line was only 0.85. And the exponential, let's display that too. Well, 0.99, so that's actually quite good as well. Okay, so use each of these 3 equations. So we did linear, we did quadratic, we did cubic, and we went a little bit further and did the exponential just to kind of see what was going on. To estimate the initial population of the bacterial culture, do these estimates seem reasonable? Why or why not? Okay, so what we're going to do for this is we're going to take the linear, quadratic, and cubic equations. Equations. So we're going to actually write these 3 equations down, and then what we're going to do is we're going to sub in 0. Okay, and we can actually do this straight on the Excel spreadsheet because it'll act as a calculator. So let's go equals, we'll go 1.1389, and let's go 0 cubed, which we don't actually even need to do, because it's just 0. So the x cubed will go to 0, this will go to 0, this will go to 0. So y equals 25.429 would be the initial population for this is cubic, initial population. And then for the linear initial population, y equals negative 142.71. Let me say linear initial population. And then for the quadratic, 66.429. Y equals, and this is going to be the quadratic initial population. Okay, so are these reasonable? So let's just take a quick look. This is negative. If you can see that negative there, this is negative 142. Can the bacteria start as negative and then go up? No, that doesn't even make sense. I would assume this is not practical because the bacteria would have to start at least like greater than 0. At least, let's go, a number greater than 0, okay, in order to grow. Quadratic, the initial population is 66. Here's the problem with that. If it's 66, it would start up here and then it would drop and then it would go back up, right? So I would say it could start at 66.49 if there was, let's call it like, there was let's call it medicine that was killing off the bacteria, and then the bacteria started to grow again. But in this case, in this situation, the bacteria is only growing. So this number is not practical, for sure. Okay. And then 0.25, this number is very practical. 25.49. Okay, and why is it practical? If we look over here, because then it will grow. Okay, it's the lowest, so there's not like a huge fluctuation there. So even if it dropped a little bit, that's still okay. It's still gonna increase over time.